Welcome to The Explainer. Today, we're diving into a really cool story about an AI that was hitting a wall trying to solve some incredibly difficult math problems, and the clever breakthrough that taught it to think smarter, not just harder. So let's kick things off with a puzzle that's been bugging AI researchers for a while. You take a state-of-the-art AI, you give it more data, more processing time, basically more time to study, right? You'd think it would just keep getting better, but it doesn't. Its performance just stops improving. It gets stuck. So what's going on there?
All right, to really get this, let's imagine we've got this brilliant AI model. Think of it like a prodigy, specifically built to crack the world's toughest math problems. But here's the thing, there's a big problem. No matter how much more training you throw at it, and we're talking thousands of hours of computer processing, it just hits a ceiling. The test scores totally flatline. It's kind of like a student cramming for a huge exam. But at a certain point, the new information just isn't sticking anymore.
You know, in the AI world, they actually have a name for this. It's called a training plateau. And it points to a really fundamental bottleneck. Just working harder, or in this case, computing for longer, isn't always the answer to getting smarter. So what is really going on? If it's not a lack of effort, what is it? Well, researchers figured out that the problem wasn't the student, it was the study method. See, the standard way of training basically encourages the AI to find an answer by trying one random path at a time. It finds a line of reasoning that looks promising and it just follows it. But if that path turns out to be a dead end, well, too bad. It often misses the correct one completely. It's just not a very efficient way to explore the huge universe of possible answers.
This slide just lays it out perfectly. The old way, the traditional training, it's like trying to speed read a textbook by only glancing at the very first sentence of each chapter. You're going to miss a ton of crucial details, right? But the new method is like creating this detailed mind map where you can actually see how every single concept connects to everything else. It's the difference between a quick, superficial glance and a really deep, systematic exploration.
And this is where a brand new approach comes in. You can think of it like a new teacher walking into the room with a totally revolutionary technique, one designed to fix that flawed study method once and for all. This new framework is called DeepSearch, and its core idea is actually pretty powerful. Instead of just following one random branch of reasoning, it teaches the AI to explore an entire tree of possibilities all at once. It does this by embedding a really powerful search method right into the training process itself. So how does it do that? Well, it uses this technique called Monte Carlo Tree Search. For every single problem, it systematically builds out a whole tree of reasoning steps. It explores a bunch of paths, it evaluates which ones look promising, it assigns credit to the good steps, and here's the crucial part. It learns from both the right and the wrong turns. And all of that lets it update its whole strategy for the next problem it sees. And the results of this new teaching method, well, honestly, they're pretty staggering. They prove without a doubt that studying smarter is way more effective than just studying longer. The AI that was trained with DeepSearch, it achieved a new record-high average accuracy of almost 63% on some of the toughest math benchmarks out there. That's at a whole new state-of-the-art. Now, I know what you might be thinking. 1.25 percentage points. That doesn't sound like a huge number, right? But trust me, in the world of cutting-edge AI, a jump like that over the previous best model is a really significant leap forward. But here is the part that really blew my mind. It achieved this huge breakthrough using 5.7 times less computational energy than the old method. It wasn't just better, it was wildly more efficient. Just look at this chart. It tells the whole story. The old brute force approach took over 1,800 GPU hours and barely improved anything. DeepSearch got a better result in just 330. That is the literal definition of working smarter. Okay, so what does this story about a math whiz AI really tell us about the future of artificial intelligence? What's the big takeaway here? Well, it suggests that a major shift in thinking is on the horizon. For years, the main path forward in AI has been all about brute force scaling. Just build bigger and bigger models, feed them more and more data, which, by the way, costs a fortune and uses enormous amounts of energy. This research proposes a totally different path. The ultimate lesson from DeepSearch is this.
A smarter algorithm can be far more powerful and way more sustainable than just throwing more computation at a problem. Better reasoning comes from a better strategy, not just more raw horsepower.
And that leaves us with a final thought, doesn't it? This breakthrough, it wasn't just about solving math problems. It's a lesson that could apply almost everywhere, from scientific discovery to global logistics. What other huge, complex problems are out there, just waiting to be solved? Not with more power, but with a smarter map. Thanks for joining this explainer.
Welcome to the Deep Dive. If you've been following the world of advanced AI, you know that large language models have, well, gotten incredibly good at complex reasoning. We're talking high-level math, coding, solving problems with lots of steps. But behind the scenes, there's this huge, really frustrating computational wall that even the top research teams keep running into. We're talking about the problem of scaling reasoning performance. You get to a certain point and it just stalls. So today, we're doing a deep dive into what looks like a blueprint for breaking through that wall. It's a new framework called DeepSearch. Now, the context here is really important. We're in the world of reinforcement learning with Verifiable Rewards, RLVR for short.
Right.
This idea where a model gets feedback based on whether its reasoning steps are actually correct, verifiable, it's been super successful.
Absolutely. It's driven a lot of progress.
But here's the catch. Researchers see this clear performance plateau. They can pour in, thousands of optimization steps, dedicate massive compute resources like weeks of GPU time.
Yeah, huge amounts.
And the performance gains just slow down to almost nothing.
Diminishing return.
Exactly. It's the classic definition. You're spending like 10 times the compute for maybe a tiny fraction of a percent improvement. So why? Why are these advanced RL methods hitting this ceiling?
Yeah, it's a great question. And what's really interesting is that the bottleneck isn't just, needing more data or an even bigger model. It seems to be fundamentally algorithmic. It boils down to the quality of exploration during the training itself.
Okay, quality of exploration. What does that mean in practice?
Well, most current RLVR methods, they rely heavily on what you could call sparse exploration patterns. Think of it like limited policy rollouts. And the model basically just follows the path it thinks is best at that moment. But the solution space for these complex reasoning problems is enormous, like exponentially complex.
Right.
So these direct rollouts, they only end up sampling a really tiny, narrow slice of all the possible ways to solve the problem.
So it's like the model is exploring a giant maze by just running straight ahead one time, hoping it bumps into the cheese.
Exactly.
Even if the cheese is tucked away down some subtle side path it never even glanced at.
That's a perfect analogy. And this creates a really weird mismatch. Because we know that at inference time, when the model's actually trying to solve a new problem, we often needed to use sophisticated, structured search techniques.
Like tree of thoughts, or MCTS.
Precisely. Monte Carlo Tree Search, tree of thoughts. These methods systematically explore the different branches and possibilities. They search.
Okay.
Yet during training, we're basically asking the model to learn these complex, search-like reasoning skills using just those simple direct policy samples. The policy itself never really learns how to search intelligently.
So it learns what a solution looks like if it trips over one, but not the process of finding it systematically.
Exactly. It doesn't internalize the search process.
Yeah.
And that lack of systematic exploration, that's the bottleneck DeepSearch identifies.
Got it. So the intelligence that gives the final performance boost at inference time, the structured search, it's treated as this separate add-on, not baked into the learning itself.
Correct.
And that separation is what DeepSearch aims to fix.
That's the core idea. The DeepSearch promise is this fundamental shift in scaling strategy. Instead of just scaling training depth, more steps, more brute force compute, which we know hits a wall, DeepSearch focuses on scaling training breadth. It does this through systematic, structured exploration that's embedded right into the training loop itself.
Okay, so our mission today is to really unpack how they pull this off. How does DeepSearch manage to take something like Monte Carlo Tree Search, which is known to be pretty resource-intensive and usually saved for inference?
Yeah, computationally heavy.
And actually bake it into the RLVR training? And maybe most importantly, how does this new approach lead to a new state-of-the-art accuracy, 62.95% for these 1.5 billion parameter models, while using way, way fewer GPU hours than the old brute force methods? That efficiency claim, that's really the kicker here.
It really is. That's what makes it potentially transformative.
All right, let's dive deeper into this core philosophy. Making structured search a training time thing, not just an inference time trick. Why is that such a big shift? What specific problems does it solve that just cranking up the optimization steps couldn't?
Well, it's radical because it changes what the model actually learns, fundamentally. When search is only used at inference, the policy learns some general rules, some heuristics, right?
Uh-huh.
But it doesn't really learn the value associated with performing a systematic search. It's still kind of relying on its potentially flawed initial guess, and the search just helps clean things up at the end.
Okay, so it's like a patch rather than a core skill.
Exactly. DeepSearch, on the other hand, uses MCTS as the main engine for generating training data. The tree structure it builds allows it to generate data points, intermediate reasoning steps, failures, successes that are much richer, much more informative than just a single direct rollout.
Yep.
And this richer information gets directly fed back into training the policy and the value functions. The model learns from the search process itself.
And we mentioned earlier, the sources are pretty clear that just scaling depth, more training steps, hits that wall of diminishing returns. There's solid evidence for that.
Oh yeah, very clear plateaus in recent studies, even with prolonged RL training.
So if just doing more of the same isn't the answer, what are the specific goals DeepSearch set out to achieve by putting MCTS into the training loop? The paper lays out 3 key objectives, right?
Yes, they formalized 3 specific things they wanted to tackle, addressing those weaknesses of current RLVR. First is expanding reasoning coverage. Like we talked about, simple rollouts are narrow. Using MCTS during training systematically explores this reasoning frontier.
The edge of what's possible.
Right. It forces the model to actually encounter and evaluate intermediate steps, even steps that might look unlikely according to its current policy. This makes sure the model sees reasoning paths it would just never generate on its own.
So you're forcing it out of its comfort zone, basically, making it explore the road less traveled.
Precisely. The second goal is delivering fine-grained credit assignment. This is huge. Traditional RL, especially in tasks with long sequences like reasoning, suffers badly from the sparse reward problem.
You only find out if you were right or wrong at the very end.
Exactly. A single 1 or 0 after maybe dozens of steps. DeepSearch, because it uses this tree structure and backpropagates through it, can assign much more precise Q values, credit or blame, to every single intermediate reasoning step along the way.
So it tells the model not just you failed, but you failed because this specific step 3 moves ago went wrong.
That's the idea.
Yeah.
It dramatically increases the signal, the useful information in the training data compared to the noise.
Okay, that makes sense. And the third objective?
The third one is really about practicality, maintaining computational efficiency. They knew that just naively throwing MCTS into training would be way too slow.
Right, it could grind everything to a halt.
Yeah, so a key part of the design is making the search itself smarter, not just bigger. They use intelligent node selection strategies and caching of solutions to make sure the computational cost of doing this embedded search is manageable and actually worthwhile. This is where the specific algorithmic tricks come into play.
Okay, let's get into the technical heart of it then. The modified MCTS framework. We know traditional MCTS, like in AlphaGo, often deals with games deterministic environments, maybe deep searches. Language model reasoning is different, right? It's generative, stochastic.
Very different.
Noisy.
So what makes DeepSearch's training time MCTS engine different? How do they adapt it?
Yeah, they made some really crucial modifications. The whole system is really built around 3 major departures from standard MCTS, specifically designed to handle the messiness of LLM generation and to really maximize the learning signal you get from the search. These changes touch on how nodes are selected, how they're expanded, and critically, how the values are backed up through the tree. Okay, let's take those one by one. Starting with Innovation A, the Global Frontier Selection Strategy. You mentioned standard MCTS uses UCT upper confidence bounds for trees and that it can be myopic. Can you walk us through why that standard approach isn't great for training LLMs?
Sure. So UCT, the way it works, is it does a root-to-leaf traversal for each simulation. It starts at the beginning, picks the most promising next step based on some mix of known quality, exploitation, and uncertainty exploitation, follows that path, picks the next step, and so on, all the way down until it hits an end state or a depth limit.
Right, one path at a time.
One path at a time. The issue for these really big, complex reasoning problems is twofold. First, it can be computationally wasteful because you keep traversing the same upper nodes of the tree over and over again.
Okay.
But more importantly, it's myopic. It focuses locally. Imagine a branch that looks really good for the first 3 steps, but ultimately leads to a dead end. UCT might pour a ton of simulation effort into exploring that locally promising but ultimately useless subtree, while completely ignoring another branch that maybe looked a bit less promising initially, but actually held the key to the correct solution. It gets stuck in local optima.
Right, I see. So DeepSearch's answer is this global frontier selection. How does that work, instead of going step by step down one path?
They look at the entire edge of the explored tree at once. They consider all the current leaf nodes that haven't been fully expanded or haven't terminated simultaneously. This is the frontier.
Okay, so how do you compare all these different nodes across potentially very different branches of the tree? That sounds complicated.
They use a carefully designed scoring function, the priority score, or for each node sealers on the frontier. This score is designed to intelligently balance three key factors.
Okay, what are they?
First, there's quality potential. This part, written as lambda 1 times parent, basically encourages picking nodes whose parent node already proved valuable in previous explorations.
So building on past success.
Exactly. And the use of tan, the hyperbolic tangent function, is quite clever here. Q values can be positive for good paths, negative for bad ones. Tan smoothly squishes these values, maybe into a range like meg to 1 to 1. This stops any single really high or really low Q value from completely dominating the selection, but it still keeps the direction positive or negative clear. It preserves the gradient information nicely.
And those lambda symbols, lambda lambda, lambda 2, lambda 3, those are just weights they can tune.
Exactly, tuning parameters to balance these three forces. The second force is the uncertainty bonus, lambda 2 times h.
Right.
Here, the entropy of the model's policy at that node.
Entropy meaning how uncertain the model is.
Precisely. High entropy means the model is really unsure about what the next step should be. It sees several possibilities as almost equally likely. Low entropy means it's very confident about one particular next step.
Okay.
By adding this uncertainty bonus, DeepSearch actively steers the exploration towards parts of the reasoning space where the model is most confused.
Ah, because that's where it needs the most guidance and data to learn effectively.
Exactly. It's targeted exploration. It makes the expensive MCTS computation as informative as possible by focusing on the areas of highest uncertainty.
So if the model is super confident about a path, even if it hasn't explored it much, DeepSearch might say, okay, let's prioritize this other path where you seem totally lost.
That's the intuition. Prioritize resolving confusion. And the third component is the depth bonus, lambda 3 times d. Complex reasoning often needs long chains of steps.
Yes,
right?
sir.
So you need to encourage the search to go deep. But if you just use a simple linear bonus based on depth, the search might just run off trying to make the deepest possible trees, even if they're nonsensical or low quality. That wastes resources.
Right, depth for depth's sake isn't useful.
No. So the paper mentions they found empirically that using a square root function worked best, something like square df dt, where depth is the current depth and ws is the maximum allowed depth.
Okay, why the square root?
It still encourages deeper exploration, but the effect gets smaller as you go deeper. It provides a gentler push for depth compared to a linear bonus, preventing the search from just blindly chasing maximum depth all the time. It balances depth with quality better.
That sounds like a very finely tuned balancing act, applying structure to manage the inherent randomness of the generation.
It really is.
Okay, let's move to the second innovation. Innovation B, expansion with entropy-based guidance. So they use the priority score to select a frontier node, then they expand it, generate the next step. What happens then? Obviously, if they find a correct solution path, great, that gets used for learning.
Right, that's the positive case.
But you mentioned the real insight is in the negative case when the expansion doesn't lead to a correct solution.
Yes, this is where it gets really interesting. If the MCTS rollout explores a branch and finds no correct solution down that path, DeepSearch doesn't just discard it. It does something quite specific. It identifies and selects the most confident negative example, which they call tech.
Wait, the most confident wrong answer. That sounds counterintuitive. Why focus on the mistake the model was most sure about? Wouldn't you risk making the model overly cautious or something?
It's a fair question, and there is a trade-off, but the rationale is quite powerful. They target the confident errors because a confidently wrong answer suggests a deeper, more systematic misunderstanding in the model's policy or value function.
Okay.
Think about it. If the model makes a mistake, but it was very uncertain about that step anyway, high entropy, maybe it was just noise, or a small error easily corrected. But if the model is confidently wrong, it had low entropy, it really thought that raw step was the right way to go.
Then that points to a bigger flaw in its understanding.
Exactly. It signifies that the model's internal representation, its underlying reasoning logic for that kind of situation, is likely flawed. Focusing the negative supervision there on correcting those confident errors provides the biggest bang for your buck in terms of learning efficiency. You're addressing the most fundamental misunderstandings, not just random noise.
So deep search is basically finding the model's blind spots where it's confidently delusional and shining a spotlight on those specific failures for correction. That makes sense. It's optimizing the learning by tackling the highest impact errors first.
Precisely. It helps the model learn more efficiently by targeting the errors that indicate a need for broader correction.
All right, on to the third piece. Innovation C heuristic score backup. This is about that fine-grained credit assignment we talked about. How do they actually assign a value, a Q value 2i's, to some intermediate step value in the reasoning chain?
So the key idea here is using a temporal decay function. The intuition is that steps taken closer to the final outcome, correct or incorrect, are generally more predictive or responsible for that outcome than steps taken way back at the beginning.
Okay, that seems reasonable. How do they model that?
They use a function like a gamma I, always max $0.21. Here the dollars is the index of the step, like step 3 out of 5, and the dolls is the total length of the trajectory, 5 steps in this case. So as a dollar gets closer to dollars, the ratio dollar approaches 1. This means steps near the end get a higher weight. The max, 1 apart, just puts a floor on it, ensuring that even the very first steps still get some minimum credit or blame. They aren't completely ignored.
Got it. So the actions immediately leading to success or failure get the strongest signal, but the earlier foundational steps aren't totally forgotten.
Exactly. And this whole credit assignment process is governed by something they call the constrained update rule, which is detailed in equation 7 in the source paper. This rule is really important for stability.
How so?
It imposes a critical constraint. Q values for intermediate nodes that are part of a path leading to a correct solution are forced to be non-negative. They can't be penalized.
Ah, so you protect the known good reasoning paths.
Precisely. You don't want the model to accidentally unlearn a correct way to solve something just because of noise or exploration elsewhere. The rule only allows negative Q values to be assigned to nodes on paths that are known to lead inevitably to an incorrect outcome.
So it preserves the good, punishes the bad.
Right. This separation protecting known good paths while aggressively assigning negative value to proven bad paths is really fundamental to keeping the whole system stable when you're integrating this complex MCTS process into an ongoing RL training loop.
Okay, the technical design is definitely sophisticated, but MCTS, as we've said, is notoriously computationally hungry. Putting it inside training loops just sounds expensive. DeepSearch claims radical efficiency, though, so how do they actually manage the compute cost? This adaptive training strategy and caching must be crucial.
Absolutely crucial. You nailed it. If DeepSearch just ran the full MCTS process on every single training example and every single step, those amazing efficiency gains like the 72x improvement would just evaporate. It would be way too slow.
Yeah, I can imagine.
So the entire practical viability hinges on focusing the expensive computation only where it's most needed, on the problems the model finds hard.
How do they define hard?
It starts with progressive filtering. Right at the beginning, they take the full training dataset, the SK teletrait, and they screen it using the current model's performance. Specifically, they look at its pass 1 at K success rate.
Pass 1 at K? Remind us what that is again?
Yeah, it's basically you ask the model to generate K different potential solutions, and you check if at least one out of those K is correct.
Okay, got it.
So they set an initial threshold, the yellow ring, and they filter out all the problems where the model's pass 1 at K success rate is already above that threshold. This creates an initial hard subset, Texart bring. The idea is, why waste expensive MCTS cycles on problems the model can already solve pretty reliably?
Right, focus the firepower.
Exactly. But then comes the really clever part, iterative refinement. After each phase of training, say, after I steps, they reevaluate the updated policy against the problems currently in the hard set. And only the problems that still fail to meet the success threshold. The paper mentions using a threshold delta to maybe 25% success with pass 1 at K4. Only those stay in the active hard set for the next round of training.
So the set of problems being actively trained with MCTS potentially shrinks over time as the model gets better.
Precisely. It's like a dynamic curriculum. The system automatically concentrates the heavy-duty computational resources on the increasingly difficult problems that the model is still struggling with.
That's smart. But wait, if you keep filtering out problems the model gets good at, isn't there a risk of, like, forgetting, catastrophic forgetting, where it loses the ability to solve the problems it mastered earlier?
That's a really important point, and they have a couple of mechanisms to deal with that. The general stability of the tree GRPO objective helps, but the more direct answer is the replay buffer with cached solutions.
Right, a replay buffer. How does this one work?
It's not just storing random past experiences. This buffer, MathCal, specifically stores correct reasoning trajectories that were found during previous MCTS searches.
Uh-huh.
And here's the key. They only add solutions to this buffer for problems that are considered hard or failure-prone specifically, problems that still fail to meet that filtering threshold after a training phase, even if MCTS happened to find a solution for it during that phase.
Ah, so the cache isn't just storing any old success. It's specifically preserving the hard-won solutions for the problems the model finds consistently difficult. It's like a library of solutions to the toughest cases.
Exactly right. It acts as a safeguard, guaranteeing that the model doesn't lose access to those crucial, complex solution paths it found earlier, especially since a small policy update could otherwise make it forget how to navigate that tricky reasoning.
Okay, so how does this cache actually save compute time?
This leads directly to the hybrid rollout strategy. This is maybe the biggest efficiency hack in the whole system. When the training process selects a problem from the hard subset, first, it checks the replay buffer.
Does a solution already exist?
Right. If a cached solution, text cached, exists for that problem, DeepSearch doesn't run MCTS again. It just uses that known, correct, cache trajectory directly for the policy update.
Okay, that saves a ton of MCTS work.
Huge savings. But it doesn't only use the cache. It also supplements that cache trajectory with a small number, beta dollars, of new direct rollouts using the current policy.
Why add the direct rollouts if you already have a perfect cache solution?
It's about balance. The cache solution provides the guaranteed high-quality success path that's exploitation of known good solutions. The few extra direct rollouts ensure the policy update is still grounded in the model's current state and capabilities. It provides a little bit of fresh exploration and helps the model adapt if its general abilities have shifted.
Got it. So exploit the known good path, but still poke around a little with the current policy.
Exactly. And crucially, only if there's no cache solution for the hard problem, or if it's a problem that just entered the hard set, only then does the system actually run the full, computationally expensive MCTS search.
Wow. So you avoid redundant MCTS entirely for problems you've already cracked and focus all that intense search power only on generating new solutions for the things the model genuinely can't solve yet.
Precisely. It shifts the computational bottleneck away from resolving known problems towards discovering new solutions for the remaining challenges. That's incredibly efficient resource allocation.
Okay, that explains the practical side. Let's quickly touch on the training objective itself, tree GRPO. How is it specifically designed to learn from this tree structure that MCTS generates, and how does it avoid common pitfalls in training sequence models?
Right, tree GRPO needs to effectively use both the node-level Q values coming from the MCTS backup and also optimize the overall policy.
Yeah.
One important piece is how it handles those Q values. We mentioned they can sometimes get quite large or volatile. So they use Q-value soft clipping.
Using that tangent function again.
Exactly. They use the hyperbolic tangent function to smoothly bound the Q values within a certain range, say -1 to 1. This prevents numerical instability, stops exploding values.
And you mentioned earlier soft clipping is better than hard clipping. Why again?
Because hard clipping, just cutting off values abruptly at a maximum or minimum, creates dead zones where the gradient is 0. If a Q value hits the hard clip boundary, the model gets no learning signal from it anymore for that particular error magnitude. Soft clipping, using a smooth function like Tana, ensures that even when values are near the bounds, there's still some gradient. The model can still learn and adjust, albeit more slowly near the extremes. It guarantees continuous learning from the MCTS signal.
Okay, makes sense. And what about the policy optimization part? How does it use the advantage function?
So the policy update is driven by the advantage function, tell and stay okay, and in tree GRPO, they introduce a specific type of normalization, sequence-level normalization. The advantage for a node such state dollar is calculated as its Q value to US state dollar minus the average reward of all the terminal nodes found across the entire MCTS tree generated for that problem instance. They call this average terminal reward under dollars.
Why subtract the average reward of the whole tree? What does that achieve?
This is actually a really clever way to deal with a common headache in reinforcement learning for sequence generation. Models learning to produce unnecessarily long outputs.
Oh, right, verbosity issues.
Yeah. If you just optimize for the absolute maximum reward, models often figure out that longer sequences give them more chances to stumble upon high-reward steps, even if the overall reasoning is inefficient or rambling.
Okay.
By calculating the advantage relative to the average outcome of the entire search tree, you're encouraging steps and paths that perform significantly better than average for that problem. It implicitly pushes the model towards more efficient, higher-quality reasoning paths rather than just long ones. It helps regularize against excessive length and promotes precision.
Got it. So it optimizes for quality and efficiency relative to what the search found possible, not just absolute score. That really ties everything together. Every part seems designed to squeeze the most useful learning signal out of the least necessary MCTS computation.
That's the essence of it. Smart, targeted search feeding into a stable, signal-preserving learning objective.
All right, we've dissected the mechanics, the clever algorithms, the efficiency hacks. Now for the payoff, the results. Did DeepSearch actually deliver on this promise of better performance and radical efficiency? What did the scorecards show on those tough reasoning benchmarks?
The results are pretty compelling. They tested it across a suite of challenging math reasoning benchmarks, parts of AIM, AMC, the math data set, Olympiad problems, really hard stuff.
Okay.
And the headline is, DeepSearch, using a 1.5 billion parameter model, achieved a new state-of-the-art for that model size. It hit an average accuracy of 62.95% across these benchmarks.
62.95%. How does that compare?
Well, you have to remember, these are tasks where pushing the needle even a little bit is really difficult at this point. That 62.95% represents a solid 1.25 percentage point improvement over the previous best model in that size class, which was Nematron V2, sitting at 61.70%.
Okay, over a full percentage point gain where things had seemed to stall out. That's definitely significant.
It is. And the improvement wasn't just overall, it showed up consistently, even on notoriously difficult subsets like the AIM 2024 problems.
But like we discussed, the accuracy is only half the story here. The efficiency claim was huge. How did DeepSearch stack up against just trying to brute force similar gains with more training?
This is where the contrast becomes really stark, and it really validates the whole approach. The researchers set up a strong baseline using what they called extended training. They took a standard method, DAPO, and just kept training it for much, much longer, adding up to 1,875 extra optimization steps.
Trying to push past that plateau with sheer compute.
Exactly. And what happened? That extended training baseline eventually plateaued at 62.02% accuracy. So slightly worse than DeepSearch.
Okay. And the cost to get there?
The cost was enormous, 1,883.2 GPU hours. Nearly 2,000 GPU hours to hit that 62.02% mark. This really confirmed that hypothesis about diminishing returns. Just throwing more compute wasn't working well.
Wow. Okay, so almost 2,000 hours for 62.02%. Now DeepSearch.
DeepSearch, using its tree GRPO objective and that adaptive MCTS strategy, achieved the better accuracy, 62.95%, using only 50 additional optimization steps beyond the initial model. And here's the kicker, it only consumed 330 GPU hours in total for that phase.
Well, hang on. Let me make sure I heard that right. Better accuracy, almost a full point higher, using 330 GPU hours compared to over 1880 for the baseline.
That's right.
That's less than a fifth of the compute time.
Precisely. DeepSearch used 5.7 times fewer GPU hours than the brute force extended training baseline, and it still got better results.
That is incredible.
It really is. And if you compare the total compute needed for DeepSearch to reach that SOTA performance versus the compute needed for the original Nematron V2 baseline it surpassed, the overall efficiency improvement factor is around 72x.
72 times more efficient.
Yes. This data just hammers home the point. Algorithmic intelligence, that systematic targeted exploration baked into training, dramatically outperforms just scaling up raw computation in this RLVR setting.
That 72x number, it feels like it changes the economics of training these things.
Yeah.
It really suggests the bottleneck was truly algorithmic, not just a hardware limit.
I think that's the major takeaway on efficiency.
And did they do checks like ablation studies to make sure all those complex parts, the global selection, the entropy guidance, the caching were actually necessary?
Oh yes, absolutely. The ablation studies are crucial for showing that the complexity is justified. For instance, they directly compared their global frontier selection strategy against the standard vanilla UCT. The global selection was more efficient. It actually reduced the average number of MCTS search iterations needed per problem by about 10.4%. So looking at the whole frontier at once, counterintuitively maybe, is computationally cheaper in practice because it avoids getting stuck exploring useless local branches as much.
Interesting. So it's smarter and faster.
Right. And they also showed the cumulative impact. They started with a basic version and added each innovation one by one. While things like the constrained queue updates and the node-level advantages definitely helped, the single biggest jump in performance came right at the end, when they added the global frontier selection mechanism.
Ah, so that was the final key piece.
It seemed to provide the largest single boost. Adding that component took the average accuracy from an already improved 62.32% up to the final 62.95%. It really highlights how important that sophisticated global allocation of search effort guided by that priority score is for getting the maximum learning signal out of the embedded MCTS.
So wrapping this up, it really feels like a clear win on two fronts. DeepSearch delivers better performance, a new state-of-the-art for its size, and it does it with drastically better efficiency.
Yeah, 5.7 times less compute than extended training for better results, leading to that huge 72x overall efficiency gain against previous methods. It's impressive.
And it's built on this tripod, really. Embedding structured search, MCTS, into training, achieving fine-grained credit assignment through the tree, and then being incredibly smart about resource allocation with the progressive filtering and tashing. It looks like a really compelling blueprint for the next generation of reasoning models.
It definitely offers a very promising direction. But as always, we need to touch on the limitations, which the researchers themselves acknowledge in the paper.
Right. What's the main caveat?
The big one is the context. DeepSearch was evaluated purely on mathematical reasoning problems. And math problems have one incredibly useful property.
Yeah.
Verifiable correctness.
Ah, you can check the answer. There's a ground truth.
Exactly. You can write a proof checker or just compare the numerical answer. The reward function, the signal telling the MCTS and the RL algorithm whether a path was good or bad, is clean, reliable, and absolute.
Okay, so why is that a limitation?
Because the next big challenge is taking this kind of framework and applying it to domains where you don't have that easy automatic verification. Think about more subjective or open-ended tasks.
Like what? Writing essays, strategic planning, maybe even ethical reasoning.
Precisely. Things where there isn't a single, easily checkable right answer. In those areas, the reward signal becomes fuzzy, uncertain, maybe even requires human judgment.
And if you can't reliably tell the good reasoning paths from the bad ones quickly and cheaply,
then the whole foundation of DeepSearch's efficiency starts to wobble. Remember how it uses the most confident negative example? Or the constrained update rule that protects correct paths? All that hinges on having a trustworthy verifier.
right, if you can't verify, you can't get that clean signal DeepSearch thrives on.
Exactly. So the big future challenge is developing effective, approximate verifiers for these fuzzier domains. Or maybe finding highly efficient ways to integrate human-in-the-loop validation to provide that necessary reward signal without slowing things down too much. That's where the research needs to go next to broaden the applicability of this approach.
Which leads perfectly into our final thought for you, the listener, to mull over. If DeepSearch's incredible efficiency gains are so tightly linked to having rigorously verifiable reasoning steps, the core idea of RLVR, then consider this. How would the development of truly domain-agnostic, reliable, approximate verifiers fundamentally change the economics of building and scaling AI? Imagine if we could confidently and efficiently verify the quality of, say, a complex policy recommendation or a novel creative concept or a strategic business plan generated by an AI. If verification itself becomes cheap and reliable across domains,
Then the compute budget required to train highly capable AI systems using methods like DeepSearch could plummet, even for subjective tasks. It shifts the main challenge, the main cost, away from just raw computational power for training.
and towards the problem of building better verifiers.
Exactly. It reframes the scaling problem. It suggests the future bottleneck might not be GPU hours, but our ability to generate high-quality, verified training data, especially for complex, nuanced tasks. The system that can generate the best labeled, verifiable data, perhaps using these approximate verifiers or clever human-AI collaboration, might be the one that ultimately wins the scaling race.
A fascinating thought. The bottleneck shifts from compute to verification. Well, thank you so much for guiding us through the intricacies of DeepSearch today. This has been incredibly insightful.
My pleasure. It's fascinating work.
And thanks to all of you for tuning in. This has been The Deep Dive. We'll see you next time.